Hello everybody, in this video I'm going to fill another gap in Rosetta code for the Rust programming language. Today's topic is Raster bars. I don't know if you know them, it's a very old demo. The explanation is quite short and this is even marked as a draft, but I coded them 25 years ago and I thought I'd give them another try on modern computers. I think I should show you how they look like. It's a quite boring effect, but back then, 30 or more years ago, this was rather cool on very slow computers, partially reconfiguring the cathode ray tube drivers and whatnot. Today it's just one effect of many, and I'd like to code this in Rust. I prepared a little hello world here in Visual Studio Code to get us started. The first thing we need is a window where we can draw things. Whenever we need something that we don't want or can code ourselves, we look at crates.io, and there's a little library called minifb, standing for mini frame buffer. Cross-platform window library. If I remember correctly, it just opens a window and lets us access the individual pixels therein, and the initial example also covers closing the window with the escape key, and a loop. I see something like an update rate, an FPS counter. I think that's quite enough to get us started. Let's first try to open a window. So minifb needs to be added to our toml file. Pick the current version. That's no longer needed. Okay, it's done building in the background. Let's just launch this example and see what it gives. Gives warnings and errors. Okay, that looks like an unmet dependency on my system. Let me fix this in the background. I'll be back in a second. Okay, that was an RTFM error. If you look a bit further down, there's a list of requirements that have to be installed on your Linux system to make this example run. And now we got a cute little window with nothing else but void space for us to fill. And this isn't even resizable, which is okay for now. That wasn't a requirement. And we can close it with the escape key. Okay, let's go back to the task description, which is very short and imprecise. When you have a look at the other code, you can see everyone is doing something else. But that's okay, we'll just try to get something along this description. and yeah, something that looks nice enough to be shared. There should be multiple bars moving up and down across the screen, or left to right if you like, swaying side to side the respective way if possible, whatever. Multiple colors, gradients, metallic looking. Okay, that's all. That's not a lot. But making some bars move up and down, which look nice and colorful, shouldn't be too hard. Okay, back to our code. Let's have a look what we have here. That's width and height. I'm not sure if that's the width and the height of the outer window or the viewport, so the black rectangle in the middle. I assume it's on the window size. A new window is created. We need a title. Title would be Raster bars. Let's capitalize them. Width and height. Some options. I think now we could add some options to make this window to allow us to resize the window. We'll have a look later. For now, that's okay. Unwrap or else, panic. So if anything fails. Creating a window might fail, for example, if you try to launch this program from an SSH terminal or something like that, when you don't have a graphic environment, for example. There's another thing, window limit update rate. Okay. That should make sure that the CPU doesn't burn out when trying to refresh the screen. It's an improvised vertical sync. As the documentation says, we are guaranteed, or almost guaranteed, to not have more than 60 frames per second. Let's keep it like that. And this is called an event loop. So the code blocks on this loop during the entire duration of our program. If you want to do something in parallel, you should move that in a separate thread. Okay, while the window is open and not escape has been pressed, do the following. Oh yes, I overlooked that line. There's also a buffer. The buffer contains one entry per pixel. Each pixel is an unsigned U32. I guess it contains red, green and blue values. Let's move that further down because it's only being used here. I even think we could move it. Do we want to move that into the loop? No, because if I move that into the loop, the compiler would always try to clear that area, which might be a bit. Now let's start with that. We're all, for the time being, we are going to start with an empty buffer, so all black. Here's another loop that tries to clear the entire buffer by writing all zeros into that buffer, and this final call makes this buffer visible. So update this window by using the buffer, some metadata to make sure this linear area is being read in the right way. Okay, let's write some color in in here. Here's a single 0, which means no red, no green, no blue. Let's write that in a hex way. Something like that. And now let's find out which component is which. Let's change this one and see if this is red or blue. That's blue. Green. And guess what? That's red. Okay, fine. U32 has a method to I thought it had a method to construct it from an array of bytes. Which would be rather handy. I think our next milestone would be to animate something on screen. Let's make something evil. Just is an ordinary counter. Oh, from language. And for each pixel, count up by 1. If you suffer from epilepsy, you should now stop or skip this video. That looks like something that is animated. Let's reset color for each frame so we get a static frame. Again, this was like that. And now we introduce a frame counter. Which is being incremented after each frame. And we use that to initialize the color. So the whole pattern should be moved to the left. That's it. Looks like a smooth transition. It also looks quite stable, that's not stopping. If there's more load on the CPU, it might stutter, but for this small example we don't care about that. Otherwise we would have to add timers, which would bloat the code and make it more complicated. And I'd rather not lose the focus on the main task. Okay, we have something that is animated. What's next? Okay, let's code a single bar. What do we need for a bar? We need a color. Let's make it yellow. You remember? Red, green, blue. Red and green yields yellow. That doesn't need to be mutable. We have a position, which is the y coordinate. Let's start at 0. This has to be mutable because those bars need to move. And we have a speed value which will be added to the position after each frame. Furthermore, we need a height. Let's randomly choose 20 pixels. Okay, that's it. Now we have to draw our bar into the buffer. There's a neat formula for addressing pixels in a linear buffer, which is as follows. Offset is y times width plus x. So we can pick any x and y coordinate and obtain a buffer for any valid x and y. If those values become negative or exceed width and height, we get some rather random results or even crashes. Crash means the program aborts because we are addressing a pixel that doesn't exist in the vector. Let's keep that in mind. For horizontal bar, we need to iterate over the y coordinates. We start with our position and end with bar position plus bar height. This y is iterating over all lines we need to color for this bar, and within each iteration we need to color an entire line. We need to compute the offset of the first pixel in that row. It's line offset, oh no, better is row offset, which is y times width. And now we need to color the entire row. For x in 0 to width. Let's optimize all this later. This is the pixel offset, which is this plus this. This is already pre-computed, so we only need to add x. Now we can access the right pixel. And we need to set a value. Let's pick this. Let's remove this garbage here. Now we should have a static bar in yellow, 20 pixel high, at the top of the screen. Yeah, and it's still red. And there's a little red line to the top, a single row. I don't know why, so look at the code. And let's get rid of the red back color. That's horrible. Okay, why is it red? Oh, it's because I entered a 1 and not a 0. Oh. What on earth? Color, height, position, speed. That should have been speed. Okay. Ugly, but works. In the next step we're going to animate this, this bar and let it move down to the bottom. Which means we need to update the bar's position. By its speed. We're going to exceed the valid range for the positions, so the programmer should crash when the bar reaches the bottom. 3, 2, 1, boom. And a good explanation what happened. So what we actually want is that when the bar hits the bottom, we negate the speed so the bar moves back up, and when it hits on the top, it should go down again. Our limit, no, the bottom row of the bar is this. So whenever, it's not exactly the bottom row, but one more, if the bottom of the bar exceeds the height. I'm not entirely sure if greater than or greater or equals needs to be in place, and let's just see if this crashes, then we know for sure. Okay, whenever this happens, negate this speed. Oh, speed shouldn't be U size. But assigned integer. Position. Let's make coordinate computations always assigned integer, even though we know this should always be positive, but it saves us a lot of edge cases. Now we have to cast the hell out of it. Just height, width, height. Oh no. They used U size. Let's fix it like that. Okay. Let's see if it crashes. It does. So I bet there should be an equals. That looks better. And now it should crash when it reaches the top. Bam. Attempt to multiply with overflow. It doesn't even let us multiply the negative value. Okay, so there's another case. If bar position is less than... Oh, no, there's a little mistake in here. We already moved the bar. Then we check if it left the screen, and here we just invert the position, but we don't invert the speed, but we don't fix the position. Let's see if that works. It does. Here's the second case for the top. If bar position is less than 0, make sure bar position becomes 0 again, and speed is being inverted again. So now it should bounce up and down. Bottom bounce and top bounce. Great. Let's try different speed. 4 times the speed. Still looking good. I just recognized that the values for width and height are the dimensions of the black box and not of the outer window. Okay, now we have one bar. Our task was to have multiple bars, and they should look nice. We see that our bar is already a bit of a compound type, so we're going to introduce a new type called bar. Having a position. Oh, I'm lazy. Color, height, position, speed. Nope. Let's create one of these bars. That needs to be mutable. Okay, here we are drawing the bar. Let's move that into a method. Draw something into the buffer, we need the buffer, which is immutable slide of color values. We need a reference to self. more complaints. Bar draw into buffer. Well, this updates the position and let the bar bounce. Position. If we want to update something, we need a mutable self-reference. Oh, no. And bar update position. Frame index is no longer needed, but I'll keep it for now. And everything still works. But the code is now easier to read, and we should now be able to easily create multiple bars. Let's make 4 of them. One in red, one in green, one in blue, bigger, smaller. Blue should be bigger. Let's make green very small. It's already red color. And different speeds everywhere. We'll let all of them start at the very top. Now we need to iterate over all bars. In bars. And let's see. That's increasingly interesting to look at. Okay. What shall we do next? I think we should make those bars look less blocky. So we need some gradient while drawing at them. Let's change this a little bit. Start and end both contain self positions, so we're going to pull that out. And removed here. Oh, that's easier to read. That's the same, but now we have access to the Y value within the bar. So 0 is the top of the bar, and that will be the pixel below the bottom of the bar. Now we integrate a function called row color. No, row, not raw. which shall return a color for each row within a bar. This is of type I32 and shall return a color which is a U32. Let's make it easy for now. Color should now be color for Y. What's your problem? Oh. That should look exactly the same. It does. And now we can decide what color to return for each row within in the bar. Let's make a simple gradient. First, let's normalize this to a range of 0 to 1 as floating point. We're going to assume that height will never be 0. Okay. Now we have a gradient value from 0 to 1. And now it would be cool to mix this color according to this value. Here it is. You can split the color into a bytes array. And now we need to decide if we want big endian or little endian. I just pick one randomly. If the result turns out to have the wrong colors, I'll just use the other thing. Let channels be this. We can also destructure the entire array. Let's assume this is alpha, blue, green, red. But actually I don't know. Then let's use our progress value. I'm now dimming the colors towards black. If Y becomes 0, all of those channels become 0. So the color is black. If Y is 1, that's the bottom of the bar, each color remains the same. So blue remains, green remains, red remains. So we should have a gradient from the top to the bottom from black to full color. Now we need to merge this again, and that was from little endian bytes. We're going to use the same order. Oh yes, we changed those values, so we need to make them mutable. Okay, let's see what happens. Okay, we now have a gradient, but we can see that blue isn't actually working. That means we've chosen the wrong one, because blue is now in the alpha channel. That's on the only channel we don't change. Blue looked unchanged, so we're going to choose big endian. And now everything is fine. Every bar is now a one-way gradient. And we can now change this value to run not run from 0 to 1, but to run from 0 to 1 and back to 0. For this to happen, we change the value to 1 minus 2 times y apps value let's make that a bit shorter, and then I'm going to explain what happens here. Okay. I think that's about correct. What we want is a function that maps 0 to 0, 0.5 to 1, and 1 to 0. The function essentially looks like this. Ramp up, ramp down, and it was this ramp up only. Let's see if this function fulfills those conditions. 0, 0.5, 1. This yields minus 0.5, this yields 0, this yields 0.5. Taking the absolute value means we have 0.5, 0, 0.5 again. Doubling the value yields 1, 0, 1, and perform the subtraction, 0, 1, 0, and that's the outcome we wanted to have, 0, 1, 0. Okay. Now those bars should look like a bar. Not metallic full, but already quite barry. We can also see that the green bar vanished because it only was 2 pixels high, and the first row and the last row are always black. That leaves not a lot to draw. Okay. So that's a good start, and I think we already fulfilled the main task. If you like, you can quit here. But I think I'm going to tweak this a bit further. to have a random number of bars, maybe make them more colorful, make them look more metallic, and improve performance a bit, because this is not really the best way to solve this. Okay, where do I start now? Let's do the metallic thing first. To make something look metallic, we also start with black. Black to the top, black to the bottom. And in the middle it should always have a thin white line. I think it's called a specular. For that to happen, we need a curve that goes from black to white, but it also has to have color in between. And that's where polynomials come into play. Let's see if I can find a good description of this curve. I'm not entirely sure if polynomial is the correct English term, or no. Let's look for the power function. I think no, power function should be better. Yeah, exactly. That's what I wanted to see. Here you can see a function which starts at 0, ends at 1. This is x squared, x to the power of 4 to the power of 8. So it always starts at 0, ends at 1, and the midpoint can be moved down by increasing the exponent, and it can be moved up by decreasing the exponent. If you draw a diagonal line, you'll note that this is almost linear steps. They're quite equal distance, and the values ramp up in an exponential manner. So this is 2 times the value of the exponent. Value doubled again. The exponent doubles each time. And if we have different different curves for each channel, red, green, and blue, we should be able to color the bar between the black and the white point. And that's what we're going to do. So we interpret the color of the bar as being a movement or a bend value for the curve. This is a bit mathematical. We'll use our mirrored y value. Let's first try this without any color, just to see if this looks metallic at all. We'll just pick this value. Use a big exponent. And now use this control value for the color itself. Let's see if this looks metallic. That's not very bad. It's a bit too aggressive, I think. Let's make it. less intense using a 5. Okay, I think the main problem is that everything gets pushed to black too far. Let me hack something into it. A little experiment to see what looks best. Okay, that could be cool. Now we need an exponent for each channel. And now that we don't use our set color in this way anymore, we only use the components thereof, so we change that to a triplet of 3 channel values. Ranging from 0 to 1, no longer from 0 to 255. Self color 0 is red. That's a bit hard to explain. As we could see here, if we change the color in a linear way, we want to change the exponents of the power function in an exponential way. That's why I picked the color, apply the exponential function, and then use that as an exponent for bending the curve. Here's a little problem. The bigger the color value gets, the bigger the exponent gets, and the lower the curve would be. So the higher our green value, the less green we have in our result. That's why we're going to negate the input. That's no longer true. That's not the exponent, that's the actual color value. RGB, BGR. Oh. And the alpha value is always opaque. Boom. Yeah. it's red. Color is known array of float values. Okay, not exactly metallic, but not very bad either. Let's scale those exponents a bit. Okay, no. Now a little offset. Oh, we're getting closer. The gray shade doesn't look good anymore. Let's remove it. Okay, does look at least a bit glossy, not very metallic, but I don't really think we need to fix that. Candy color. Another thing I noticed, we have a bar in aquamarine, which wasn't our intention. We had red, which is this bar. This should be red and green, but instead we got green and blue. Let's switch down to little endian again. Otherwise, I could reverse the order of that array. Oh. No, wait. Big endian is good, but red, green, and blue need to be in other different order. Okay. Now we have back our yellow bar. Still feel those exponents are becoming too big because the white line is very thin. Looks like glossy plastic to me, but I think it's okay. We're going to add some ambient color, so the outer black isn't too black. Okay, I think this is okay. You can even see the very dark gray line, which should be the green one, but it's too small to show its color. Now for the performance thing. The animation we've seen is actually a 1D, one-dimensional animation, because every column in the picture looks exactly the same. What we are doing here is quite expensive. We are doing a few exponential calculations, power functions, multiplications and whatnot, even a division here. And we're doing that for every single pixel. That's quite some waste of CPU power, while it would be enough to compute a single column of the entire image and clone this column from the left to the right, and that's exactly what we are going to do. We're going to rename this function into draw column. We're going to remove the for loop, just going from the left to the right, and replace this with let x is 0. Remove x. Remove offset. Row offset no longer needs the width. The width is always 1 because we only have a 1 pixel column. This is short enough to be moved in here. And this is short enough to be moved here. And this should be an iterator. If this is a, let's call this a column buffer, and what we are doing here, we are replacing or setting a list of consecutive indices, which is nothing else but a subslice starting from self position to self height. We want to change those pixels. Oh yeah, for indexing we need year sizes. I might move that out of the statement. We need an iterator over each entry. I bet there is an easier way to replace the entire content, but for now I do it like that. The problem here is we no longer have the y coordinate within the buffer. We can get this back by using enumerate. Now we have the row index. in our closure. And the color. Okay, that should do the same. Row index. Oh, I keep pressing escape. Slowly press enter. This happens when you switch IDEs. Okay. Now the color needs to pass a column. With the height of the picture. And in the next step we need to clone this column into the entire into the image. Now even better, we iterate over the column buffer. Oh, this might be fun. As we're going to write an entire pixel row at once, we could cut the buffer into rows using the chunks method. Using a chunk size of the image width. So this is an iterator that gives us access to a single row at a time, the entire row. And we can zip with this the column buffer. We have the row and the color, and now we can row their fill. Perfect. Yes, that should be extremely fast. There is still room for optimizations. It would even be better if it works. It does. And now the complicated computation for each color is only performed once for each row of each bar. And that's a really cheap thing now. But I just got another funny idea. We could use the column buffer, iterate over that. And use each value to create a new iterator. I'm going to explain this in a second, if it actually works. Oh no, not a map, a flat map. Flat map. Buffer is being used here. Okay, we need a type hint. Let's place it here. It's a bit better, a bit easier to read. Okay. I'm going to explain this if it actually works. Yes, it does. Okay, that's really neat. So we are iterating over the colors of a single column. For each of those colors, we create a sequence where this color is being copied as often as the image has pixels to the right. So this is copying the single pixel into all pixels of a single row, and then we concatenate, so, or in other words, we join all those sequences and collect the results in a single big array. And then we use this array to draw the image. Yeah, that's it. I'm going to write the documentation later. That's nothing for a video. Okay, something that could be improved is that those speed values are integers, so we don't have any speeds in between. This is the slowest speed, this is the second slowest, and so forth. We couldn't have any speeds in between, so I'd like to make those values a float value. Let's make everything 10 times slower, and the last one will be brought to an original speed. For that to work, speed needs to be float. We need to make sure position is a float as well. Height would remain an integer value because we are drawing whole pixels, and then we follow the red lines. If position is less than 0, make sure position is 0. If position plus... Okay, now it's becoming interesting. Because we're mixing float and integers again. Oh dear. Let's see if we can change this later. And yes. Okay, that's all. Okay. Let's see if it crashes. Nope, it doesn't. Here's the second line. Third one. I'm not going to wait for the yellow one, don't worry. Okay, no crashes so far. But now that we are working with floating point values, boundary checks against integer ranges are becoming a bit problematic. I'd rather make sure that the draw method doesn't crash if those values aren't safe. How do we do with that? Start row as self position. First round the value to an integer, and then clamp the value to a valid range, which is 0 to height. Yeah. already have a good value. Okay. Okay, that range needs to be in a U size. We cannot make that into a U size because it could be negative. Let's make this here. Oh, this is getting really annoying. Let's make height an on-site value. So we can certainly convert that into a U size. So now start and end. Are representing a safe range. Okay, now we don't need to worry about running issues when checking the boundaries of the bounces. Okay, here's another. Let's check if everything works. Oh, let's speed up a bar beyond everything. Speed is 10. Okay. At this point we are doing two checks if the bar is outside of the bottom or the bar is outside or hit the top of the window. But we only need to check one of both depending on whether the speed is positive or negative. So we could speed is a little trick to match on the sign. No, wait. I hate you. Floating point comparisons. Great thing. Let's see if there's a sign which is 1, -1 or 0. You know what, I'm going to ignore all those special cases. Keep it simple. Okay, this is downwards movement, so we only need to check for the lower bound. This is an upwards movement, we only need to check for the upper bound. This is a complaint that we could collapse the else and the if, but I don't think it's very readable. Let's introduce a new variable called limit. Which is the maximum value the bar is allowed, the maximum position the bar is allowed to reach. If the bar hits this limit, going to so if the position is greater than the limit, the bar will be bounced back by whatever amount it crossed the limit. So if it's 10 pixels behind the limit, it will be flipped to 10 pixels before the limit. That's only relevant for very high speeds, and if we ever introduce a timer which makes sure that there are bigger and slower jumps between all frames. Am I totally sure about what I'm doing here? That's easier to read. So position is greater than limit. So I compute the distance, how much too great it is, and subtract that from the limit. I'm going to do the same here for symmetry. If position is smaller than the limit, this boils down to 0, 0, so it's becoming minus position effectively. But the nice thing is that now we have two identical code fragments. Maybe we can save some code. Not in a very readable way. Let's try how good this is to read. We're going to introduce bounce position. Which is some value if any bounce has happened, and as a non-value if there wasn't a bounce. And we're going to return the new position. the bounce position and check if there were any bounces. So if let some position, no, it needs to be removed. Okay, this essentially means position after bounce. Okay, if a bounce happened, please update the position and invert the direction. No, that's not too bad. That's a cool trick, using Boolean expressions. To convert Boolean expressions into an option. Those have been added lately. Oh no, it's unstable. What about then? Oh. Oh, then is not unstable. Let's use that for now. No, I don't think it's worth making this even more compact. Let's hold it like this. Well, equals. Okay, I don't think that's too hard to read, and maybe it even works. Yeah. That's a very cool thing on Rust. Whenever you make it through the compiler, you can be pretty sure that the program does what you want. And that's frightening sometimes. Okay, let's get rid of the frame index. So this tool looks a bit messy. This is rather clean. Let's make that speed bar a bit slower. Let's make that one a bit more visible. Okay. We could also make those rows blend with each other. That was, that would even look better, I think. I'm still not very happy with the look of those bars. Oh no. Oh, what the hell? No, 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 no. Oh, let's keep it like that. Let's make that a bit more compact. Now the result value lies between 52 and 252, which is exactly the range for an unsigned 8-bit integer. Round SU8. That allows us to remove that entire block. That's too grayish. Let's make okay, that's better. Okay. Okay, let's keep it like that. I think I'm gonna write some documentation and upload the whole thing to Rosetta code. Yeah. If you have an idea what I should or could do next, please have a look at Rosetta code, and there is a list of open tasks. No? So that's Rosetta code. Scroll down to unimplemented tasks by language. Find Rust, and here's a list of things that could or should be integrated. If you have any ideas, let me know. I hope I didn't bore you to death, and yeah, stay tuned, give me a like if you like it. If not, leave a comment what could be improved, and see you next time.